So hello everybody. So this morning we have a research talk and a tutorial. So we start with the research talk by Blake Bordelon. So we met Blake yesterday. So he's going to talk about training dynamics in large networks from the super wide to the scaling low regime.
Thank you. Thanks so much. Thanks for the introduction again. And yeah, so thank you everyone for showing up after yesterday. So I know yesterday we were doing this tutorial and we were like trying to learn some ideas in DMFT and random matrices. And today we're going to try like applying some of those methods and ideas to get insights into training more realistic neural network architectures. Okay, so I'm going to start with just like what I'm going to call the super wide regime, which is like taking width to infinity first with everything else kind of held fixed, training time, batch size, things like this. This is kind of the regime that Mufon was mentioning first. And then I'm going to try to, as Mufon alluded to, there's some sort of toy models that exist out in the world that people can study. Regimes beyond that behavior, where you can start thinking about like finite model size effects influencing dynamics in a meaningful way, and basically giving toy models of scaling laws. So I'm going to mention those after. So what are scaling laws? So there's just kind of empirical regularity in a lot of deep learning training paradigms, where across a bunch of different like data sets and modalities, if I train models of different sizes, so each line here is a model of a different size. So this is a small model. If I train it for a long time, it'll eventually saturate in performance because it has like limited capacity. If I go to a slightly larger model, it'll get to a lower loss before it saturates. So if I plot a bunch of different models of different sizes, you can see that there's kind of a Pareto frontier, like a compute optimal envelope that I'd like to follow. And so this is known as the compute optimal kind of neural scaling law. So we'd like to kind of understand this, but to understand how this works, we also need to understand like how models are being scaled up. And I just want to mention that the scale of these things is really crazy, and it's getting crazier almost every month. So for example, so this Claude Mythos model is rumored to have about 10 trillion parameters. Now it's not a dense model, it's a mixture of experts model. I'll talk about what that is. So only a subset of the parameters are active for any given token. But does anyone know, so like we just had this Artemis 2 launch, so like NASA did this thing recently. And it was a cool sort of rocket ship going around Mars. Did anyone know how much this project costs? Anyone know? So it's about $4 billion US. And training a 10 trillion parameter model, if you just do a back of the envelope calculation, it's about $10 billion probably. That's the estimated cost. So we should really think about like modern pre-training runs, especially at like the very frontier scales, as moonshots. So you really want to make sure that these things are stable and predictable and well behaved, and that you don't want to waste money. So this motivates kind of having a good understanding of kind of optimization dynamics and like very large neural networks trained on lots of data. So that's the kind of goal. What's hard about this is, I mean, from a mathematician or a physicist point of view, these systems are really complicated. There's a lot of different constituent components. The optimization landscape's in a multi-layer network because there's products of all these parameters. It's a non-convex optimization landscape. There's a lot of different kind of architectural details. So like you could be in a fully connected model or a model that has sort of weight sharing across spatial positions, like a convolutional network. Or you could have, in more recent models, transformers, like attention layers that do interesting processing across the token stream. So I mean, there's a general question. So when people say, okay, I'm going to take my model large, what does large mean? Right? There's different ways to make the model large. You can make the model deeper by adding more layers. You can make the model wider by adding more neurons per layer. So what do we mean by large? And then the second question is like, at what scale do you start maybe like seeing some kind of macroscopic behavior emerge? So, you know, we just have these microscopic parameter adjustments, like every neuron connects to every other neuron in this layer. Those don't really tell me much maybe, but maybe there's collective properties of the entire network that govern learning and govern basically the evolution of the output of the model. So we want to understand that. So as Mufon alluded to, right, there's not just like one variable, there's many potential ways that we can think about scaling. There's, you know, width, depth, data, hyperparameters like learning rate, there's training time, how long you train, like token horizon, and other properties, other hyperparameters like initialization scale. So the first thing I'm going to talk about is how do we scale up to get like a well-defined infinite width or depth limit. I'll describe basically a couple of just rules and try to connect it to the DMFT ideas we presented yesterday. But roughly the idea is something like the following. So the neurons in the hidden layer of the network, you can think about them as a particle, like an interacting particle system at finite n. But as n goes to infinity, they interact weakly, and they are only, their dynamics are only coupled to sort of population averages. So the empirical measures over the neurons are all that each neuron sort of feels. And so what we want to do is we want to go from just sort of standard vanilla MLPs up to maybe transformers with MOE blocks by the end of the talk. So that's the goal. And it's not a priori obvious how to sort of scale up in order to get a well-defined limit. What ways can you scale up to get a limit? What are the rules that are allowable? And then a practical extension or a payoff would be like if we can stabilize training across scales, if we can make things more predictable, maybe certain properties of the optimization landscape will be stable across model sizes. So we might be able to do what's called hyperparameter transfer, where good combinations of hyperparameters like learning rates at small model sizes will transfer to sort of larger model sizes. So I wouldn't have to retune the model as I keep getting bigger. Okay. So the claim is that if you properly scale a neural network, so if you properly scale the width and the depth and other architectural details and learning rates and things, there's sort of a universal in this. So in this talk, I'll describe what I mean by universal. So a family of joint scalings of width, depth, and other things and learning rates can converge to the same kind of output dynamics as I take everything to infinity. Okay, and so the dynamics in this limit are described by an evolving, I'm going to call it an evolving representational geometry. So these are these correlation matrices that I talked about yesterday. So these are like these feature data-data correlations in the hidden residual stream of a transformer. And so this is at initialization, this top row. This is like some base model. This is some just model you start with. Then I can double the number of heads. I could double the number of the size of each attention head. I could quadruple the width, or sorry, the depth. So these are the initial kernels. So this is a data by data matrix. So the colors represent like how correlated these two data points are on the residual stream. So when I pass these embeddings forward, what's the dot product basically? And you can see that I start here, and then the kernels are dynamic. So the kernels change. They start from this kind of more or less unstructured thing that just depends on the input statistics, and then they pick up this blockwise structure that's related to the class identities of the data points. So they're doing feature learning. But the feature learning is roughly consistent. Like the final kernels I get is very consistent kind of across scales. And the optimization trajectory, if I scale things correctly, are also very consistent. At least the early time dynamics are very consistent across model sizes. Okay, and so this is a story about convergence at early time. And then scaling laws we're going to see is once you do this proper scaling, scaling laws will be about the finite size deviations from the limiting dynamics. So how close is a finite model to this well-defined infinite width limit? Okay. So this is just to point out how you scale up matters. So like, people used to talk about a bunch of different kinds of infinite width limits. So Mufon mentioned this NTK limit yesterday. So let's say I started with a model that was this width 64 or 64 channel convolutional network. So let's say this is my like base model. I could scale up using this update rule where this gamma parameter is order 1 and constant learning rate. And as I go wider, the training dynamics actually slows down. So the models are kind of not training, they don't have kind of consistent learning curves. And the reason it's slowing down is because the inner features are sort of freezing as I go to larger and larger width. Okay? And so increasing the width in this NTK parameterization, like at a fixed snapshot of time as I go to larger thing, it could potentially lead to worse performance because you're sort of freezing the kernel evolution. Okay? If you do this, what's called mean field or mu-p scaling, this is an alternative scaling where you instead treat this, this output scale multiplier like order square root of n times a constant. If you do this, then you can see that all the models actually they obey very similar learning curves. And if anything, like this, the wider models are slightly better. Okay, so this is just to say that choices kind of matter here. You have choices of different parameterizations and different limits, and they behave differently across finite sizes. So we want to try to find things that are representative so that the finite models look like the infinite models. In mean field behavior, basically we want to say that this is a better representative of this initial model we started with. So we want to kind of converge to this limit and think about it. Okay, so let's talk about the width limit. Okay, yesterday I introduced this idea of DMFT. So the idea was you have a coupled system. We had the spin glass example. And the coupled system at finite size, when I take a limit, and this J, let's say, is just a random matrix with symmetric entries. So this is just this is the P spin model with P equals 2, and the example yesterday. So the claim is if I take width to infinity, or like number of nodes in the system to infinity, I can replace this with a little single site stochastic process. So one variable dynamical system S that's taking in a colored noise process. So the colored noise process I'm going to try to box is these green or these teal kind of things. And then the self-feedback through the response, I'm going to indicate with these magenta boxes. Okay, and so that's the rough schematic. The claim is all sites decouple. So instead of thinking about all these sites coupling to each other, I can think about a single node in the system that's driven by a noise process and couples to itself through some memory term. Okay, so I paid this cost. I go from infinite dimensions to 1 dimension. The cost of doing that is I introduce this non-Markovian process to the dynamics. But after I do this, I can obtain everything I need. So the covariance of this noise is in fact the same as the correlation I would get if I computed the 2-point function of this S. And the response is what I'd get if I kicked the right-hand side at time t prime and measured the response to the same site at time t.
So what's the nature of this coupled noise? I mean, sorry, this colored noise. Do you explore an entire spectrum of noise to see what the dynamics is from one particular type to another particular type? How do you choose that?
So it's determined actually by the same equation. So the statistics of this noise, so it's Gaussian process, and it's a Gaussian process with a covariance that's actually the same as the covariance of the S. So it's a self-consistent equation. So it's like suppose I knew this covariance of S, then I could sample or I could characterize this distribution. Then I could close this equation. I could integrate this equation and calculate the second moments of S, and that would be a function that would have to recapitulate that same C. So it's an equation of the form C equals some function of C, if that makes sense. So some people call it self-consistent dynamical mean field theory. Yeah. But if you start with some well-specified boundary condition and integrate forward in time from some initial condition, the equations are causal, so you can get a unique answer. Things only become very self-consistent when you make these like ansatzes, like the ansatz I made yesterday about like the time translation invariant solutions or something. Okay. So my claim is, and I kind of alluded to this yesterday, and I did it kind of quickly, so I'm not sure how much it landed, but the claim was, if you take a deep MLP or a deep network, with L layers, and let's just for the moment think about L as fixed. And I take width to infinity, okay? And this is going to be what I'm going to call the super wide regime. So the super wide regime is I'm taking width to infinity in this mean field scaling, or this mu p scaling, but I'm keeping batch size and training time, so B times T, which is the total data that you see. I'm going to keep that large but fixed. So this is a fixed number, but n is going to infinity. Okay. So the claim is if you do this order of limits, you can replace every hidden layer with a forward variable h, which is like the typical h variable. You can think about it as one random draw from one of these neurons in this hidden layer. And its corresponding backward pass variable g. So this is a gradient that I'd get by going backwards through the network. So this g I would get from backprop by doing df, derivative of f, with respect to the hidden state. Okay, and so these things couple. They have Gaussian noise terms that drive the system. So these are colored Gaussian noise processes in this teal. And then they have a cross feedback. So the h feeds back through some response function to g, and the g feeds back through some response function to h. Okay. And then what do I actually care about to calculate the evolution of my function? I just need to track, at least in gradient flow, I just need to track what I'm going to call dynamical feature kernels. So that's the correlation between the states at layer L at data point x at time t with the same layer at data point x prime at time t prime. So what is this average? This average, I can think about this average as an average over the neuron distribution, or an average over the layer, as one way to think about it. And there's a corresponding gradient kernel, which is the correlation of these gradient fields. And then the response functions are like these things where I kick the right-hand side and then I measure the effect. Okay, so you could view this as writing down kind of like a stochastic process, but you could also just say, hey, train one very large neural network, plot the histogram of activity. So plot the histogram of these h's, and compare that to the distribution I got from this mean field equation. Okay, and so that's what I'm plotting here. So the colored lines are one histogram of one really big wide network. And then the dashed lines are what I get by integrating these mean field equations driven by this colored noise process. And so you can see that they match, right? So, and the claim is basically that asymptotically, as n gets large, this joint measure on n neurons is factorizing into like a product measure. So each neuron's IID. And okay, again, the equation doesn't matter, but it's a teal Gaussian process, and then it's a feature learning correction that's non-Markov that's capturing all these effects. So that this is the effect you get from learning the features. And so Yeah, okay. And then let's say I wanted to track in gradient flow how the function evolves. So I want to characterize, let's say, the inductive bias, like what kinds of functions do I get when I train in this regime? Well, suppose that I solved for the evolution of these correlation functions. I can just sum over the layers, the gradient kernel and the feature kernel. And then this is a sort of closed equation for the evolution of f. So I can get dl df. This is like, for example, for mean squared error, this is y minus f. And then for yeah, these are, you can see that this is this object is actually known as the neural tangent kernel, but you can see there's a t index on it now. So it's evolving, so the NTK is evolving over time in a way that's governed by these phi's and g's. Okay.
So you said that you want to keep training time order one with respect to everything, right?
Yeah, at the moment I'm doing that, yeah.
Why can't one keep going?
So one can't keep going because you need to control the fluctuation. So you need to control the finite size errors of these things. And the finite size errors of these things compound as time and data grow.
So size meaning n?
In width, yeah. So for example, if I took batch size much larger than width, then the kernels that I'd try to compute here, the empirical kernels would actually be the low-ranked matrices. There would be a null space that I'm not capturing, whereas the infinite width limit, there's always I'm always able to kind of resolve order B directions if batch size is B. So it's a question about like whether or not these things are low rank, and also how the central limit theorem kind of noise corrections from the empirical averages over neurons converge to the population measure. So that also, those errors also can compound. I'll talk a bit about finite size effects in a little bit. And there's toy models where we can go beyond this. Yes?
You just recall what delta is.
Oh, sorry. This delta object is exactly this minus derivative of the loss with respect to f. So this is just so you can do like cross entropy or something else besides mean squared error. But for mean squared error, just think about this as y minus f. Okay. Yeah, and I also just want to stress, like neuroscientists think a lot about these kinds of data by data correlation matrices. So this is a common tool to analyze neural representation. So it's like, if I look at a monkey brain and my brain, there's no reason I can like match neuron for neuron, like the representations, but maybe the cross correlations of neural activity across pairs of data points might have some meaningful structure. And indeed, like if you present a bunch of different images of, let's say, natural things, animate things and inanimate objects, so this is a bunch of different objects, and you plot the cross correlation of like neural responses in a human inferior temporal cortex, which is a part of like a very high up conceptual kind of component, part of the visual ventral stream. You compare this to what you get when you train a deep convolutional network on natural images, or you can also compare it to the monkey inferior temporal cortex, and you can see that they're not exactly the same, but there's some shared structure that's sort of interesting and suggestive. And so, okay, the implications of our little toy DMFT thing and artificial networks is like maybe if you really wanted to characterize inductive bias, you can't just take snapshots. Maybe you need to understand how these things are evolving. So time by time correlations might be important. Okay, we discussed this in this little review. So you might have heard of NTK. So I had this output multiplier. So okay, each color is a like large but finite network, I think width 1,000. And the gamma is basically a knob that can take me from the lazy learning regime to the rich learning regime. So you can see that modifies the dynamics. So at initialization, the gradient is the same, but over time I accumulate feature updates that speed up the dynamics. And you can see that the density for this pre-activation goes from Gaussian in the lazy limit to something non-Gaussian and complicated for this ReLU network. But the theory is sort of tracking it. And then you can see that as I turn on gamma, I'm getting more and more of this like clustering of my in my data space. So my data correlations are becoming more. So this is a binary classification problem. So like some of the data points are in the same class are getting higher similarity than between classes. Okay. So this is just saying you can go from this kernel or NTK kind of regime. Then there's this intermediate regime where the weights really look like this bulk plus spikes picture, and they're on the kind of same order. And then there's this other regime. If I took gamma super, super large, there's this kind of neural collapse regime where I've forgotten about the component from randomness, and I've just sort of fully aligned to the labels, more or less. Okay. I'm just going to go through this quickly because I mentioned this yesterday, but we had this kind of weight space picture. So what's happening in weight space? Well, there's this bulk, this random part, which has Marchenko-Pasteur singular values. And then we have a collection of spikes. And the number of spikes, I should say, is really batch size times time. Right? That's the total number of spikes that you could get. But in fact, these things are kind of correlated across steps, and they're also potentially correlated across data. So the effective rank can be lower. So this is just showing this kind of behavior where at initialization, everybody follows the Martin-Pasteur law. Okay, at time 100, you can see maybe some outliers starting to emerge. But then across different widths, these different colors are different widths, there's very consistent outlier dynamics, right? And that's good. That's sort of suggesting we're behaving similarly across model sizes because we've done the mu-p scaling. Okay, cool. And this is the theory. So this is this like theory that I described yesterday. You can predict the BBP time. So when does the first outlier kind of emerge? So this is the maximum eigenvalue of, let's say, one of the hidden weight matrices in like a depth 4 network. And so you can see that like for the first layer, there's one learning curve, and then the second layer, there's some other escape time. And the escape time has to be determined through that like zero determinant secular equation that I presented yesterday. Okay, cool. We talked a lot about width. What about depth? So I'm going to talk a bit about ResNets today. So MUFON had a very nice talk about proportional scaling in feed-forward networks. And there was an interesting Brownian motion process over the kernels. I'm going to study a slightly easier problem today, which is this problem of skip connections. And so when you have skip connections, then basically the thing that's learnable is this like this branch, this residual branch. So you have these weights W here that we're going to start at random and then train. And we're going to look at configurations of this system where this L to the alpha is downscaling the residual branch, and this alpha is some number between 0.5 and 1. Okay? And we're going to have different limits depending on what alpha we choose and different descriptions of the dynamics. Okay. And the result is we're going to get some kind of dynamical system over neurons and over kernels over both the training time and this sort of internal layer time. Okay. And like MUFON presented this idea of layer time very well, so I think that should be intuitive. But let's do a warm-up. So let's just say everything's at initialization. So let's imagine the W's are all random and fresh. So each W is independent, IID, random variable, a random matrix. So the claim is, the claim is through training, actually, all of these sort of, quote, DMFT observables, so all the correlation response functions, the output of the network, all the things I said were self-averaging at the mean field limit, they have some joint width and depth scaling, and this is a commutative limit, so it's sort of nice. And okay, let's look at let's get some intuition just from initialization. So let's say I'm at initialization and all these weights are random. Well, what I can do is let's define capital H to be the second moment over the neuron distribution. So like this is going to be the variance of the neurons for like one single data point. And we're just going to try to track how this variable evolves over the layers. So you can just kind of guess the recursion here. So like let's say this is independent of this. So let's calculate the second moment of this thing. It's going to be this HL plus and then this thing squared. So beta squared over L and then an average of phi of H. So suppose I knew H of L, I can plug this in and I can do this sort of nonlinear average. And that gives me this new HL plus 1. So it's a nice recursion. And the single neurons themselves, you could think about as sort of stock prices. They're kind of following this rough kind of geometric Brownian motion thing. But the kernels are smooth. The kernels are evolving in terms of this difference equation. And you can kind of stare at it. So it's sort of like an ODE for the kernels with a 1 over L kind of step size. So this should have an ODE limit where I replace things with a derivative of some effective layer time. And I can integrate. So this tau is a layer time that goes from 0 to 1 over all the layers in the network. And then if I wanted the NTK is this G thing times this phi L. And again, you can see this is kind of an average, or this will converge to some kind of integral over the layer time. And indeed, if you plot this across different L's, do the signal propagation, you can see that it's for a ReLU network where two inputs have like angle theta apart from each other. This is converging to some kind of well-defined autocorrelation as L goes to infinity. Yeah. No, yeah, so no. So all I'm doing is saying that both have to go to infinity here. Yeah, so what you can do is in this particular setting, for this model where it's, so the trainable, so this is slightly different than the model I'll present in a minute, but in this model you can see that each branch is linear in the weights, if that makes sense. And in this thing, you can show actually the depth and width. So you could take the depth to infinity limit of your, let's say, DMFT action, and then do a saddle point for large N. That gives you the same answer as if you had taken the saddle point and then studied the large L behavior of that saddle point. So you can, the limits commute, which is kind of cool. And okay, so this is just flashing again, teal box, magenta box, right? Brownian motion, but now there's Brownian motion across this layer time, which is layer index over all layers. And then there's this feature learning correction in this magenta. Okay, and the Brownian motion is sort of local. It's local in the layer time, but it's non-local. It's tracking the same kind of correlation, the data-data, time-time kind of correlation structure. Okay. And again, the kernels are still averages, so I have to compute the equal layer correlations for different pairs of data points and different pairs of time points. And as Mufon alluded to, how is a finite depth network different than this network? It's a discretization effect. So for depth, at least, that's sort of the main thing. And the step size, at least in so in kernels, the step size, for the kernel objects, the step size is 1 over L for an ODE. But it's like I have a d tau for my SDE that's also 1 over L. Okay. So what's a nice result? So there's this nice work by Greg Yang and colleagues at Microsoft where they argued if you could figure out a good scaling recipe, you should hope for, and a good scaling rule that maybe converges to a limit, you should hope that there is a chance that learning rates or configurations of hyperparameters in small model sizes would, quote unquote, transfer to larger model sizes. So what we wanted to do is say, suppose that problem is solved for width. It's not solved for depth in the naive thing, right? So if I just have a normal ResNet without any branch scale factors, and I train with SGD, so this is a nice plot from Lorenzo. If I sort of go from a depth 6 model to a depth 30 model, at some point there's some missing dots here that indicate like runs that diverge because of instability. So somehow the models are becoming harder and harder to train at larger depth. But I would like to train a deeper model and a wider model because they seem to be doing better as I go to deeper and wider. So then, okay, our procedure, our protocol, if you adopt sort of the mean field scaling over width and depth and do this scaled branch trick, you can see that the optimal learning rates are actually pretty consistent across all the widths and depths. And you can jump from like a width 128 depth 6 model all the way to like a width 1024 depth 30 model, and the same learning rate is working and stable. That's good. Okay, cool. So this is nice. This could save you money because you don't have to retune everything as you go to bigger things. Okay. Those were very simple MLPs, right? We train, in language modeling at least, we train with sort of complicated blocks, right? We have these multi-head self-attention blocks. Who's heard of, okay, just raise, if you've heard of attention. Okay, cool, okay. And who's heard of mixture of experts? Okay, people know. Yeah, so okay, in practice we have these more complicated blocks. We have a residual stream, and we could just also do the same kind of trick. So we're going to try to do something over L to the alpha, right, for the depth scaling. And then we got to figure out how to do width scaling for these kinds of things. So that's what I'm going to try to figure out. Okay, so an attention block, multi-head self-attention schematically, right? So this is for like, I'm disregarding kind of token dimensions. I'm just trying to visualize like the size of the vectors. So for every token, right, there's a key. For every other token, there's like a query vector. The vector for each head is of size, let's say, in H. So that's the size of each head. And then I have H heads in parallel. Each head computes an attention score. So this will be a matrix that's sequence length by sequence length. So there's a sequence length by sequence length matrix for each of the heads. And then I do a linear combination of the values against these attention weights. And then I map back either through concatenation and then some linear layer to some output back to the residual stream. And the residual stream, let's say, is dimension n. Okay? And a mixture of experts block is very similar to this. So the idea is like, instead of having a full dense MLP, I'm going to sparsely activate some subset of the MLP. So you can imagine I break the MLP up into E experts of size NE. And then instead of activating all the MLP dimensions, I take the top K out of E of them. So I train some router, and the router needs to learn, just like how here I train some attention weights for keys and queries. Here I train some router weights, and the router weights need to learn which tokens get routed to which expert. And then I only compute the expert MLPs for the top K, and then I map back through a linear layer back to the residual stream. Okay. All right, so how do you choose the depth exponent? So these blocks that I just described are nonlinear in their parameters, so they're more complicated than the toy model I just presented that converges really quickly. So it turns out you can get a feature learning limit in the sense that all the residual stream preactivations move by order 1 by choosing any alpha between 0.5 and 1. But in practice, so this is with some guys at CRiSM and with Mufon and Lorenzo, In practice, though, if you do the alpha as a half, you can see that there's sort of not very good learning rate transfer. So as I go from shallower models to deeper models, the performance gets better, but the optimal learning rates are shifting to the right. So the finite depth models are not good representatives of the infinite depth limit. And I don't really, so if I jump from the small depth model to the big depth model, I don't really have a good control over whether this learning rate is going to be good or not. And then what we're calling complete P is this choice of alpha equals 1. And in complete P, which, yeah, basically in this scaling, you can see that the optimal learning rates are roughly consistent. And also, you can go even beyond optimal depth, or like you can train super deep models stably if you do this, whereas these things can kind of, the normal, like standard parameterization and alpha as a half can kind of destabilize. Okay. So why is this happening? So let's say instead of a linear layer, so before we had a W dotted into some phi of H. Let's just say I had imagined I have some nonlinear function of the parameters in this block and the input residual vector H. Okay? So we had an earlier paper where we looked at a bunch of different kind of like scalings of attention transformers. And so basically the claim is if I want this update when I do a feature learning step, so when I do a step on theta, I want this whole thing to contribute 1 over L. And the reason is that the backward and forward features from DMFT are correlated, they're strongly correlated across layers. So I need actually, the initial thing can be 1 over square root of L, but when I do a step, the update needs to give me something that gives me 1 over L in front. Okay, so to retain nonlinearity, so to retain a nonlinear function through steps of training, I need actually alpha to be 1. So if I do what I'm calling the SDE scaling, which would be alpha as a half, I get local linearization. So what does that mean? So it means I can take the block and I can do a Taylor series around theta 0 because the change here is like L to the minus a half, right? So I get basically one term that looks like Brownian motion and then one term that is of size, so there's a prefactor 1 over square root of L, and then this is changing by 1 over square root of L. And then the higher order corrections are suppressed. Okay, so the claim is as L really goes to infinity, I get the Brownian motion, that stays, but also I just get an update per branch that is linearized around the initial parameters for that branch. So it's not a kernel method in the classic sense, but it's like locally a kernel method. So like locally, like the res block is frozen. But the neural ODE kills the Brownian motion. So if I do 1 over L, it kills this term, but then all the higher order terms sort of survive at order 1 scale, because theta minus theta 0 is order 1. Okay. And both of these learn features in the sense of delta H is 1. So we kind of introduced this new notion of complete feature learning. So don't lose any nonlinearity in any subblock of the network. So just like be maximally nonlinear if possible. Okay. So nothing should asymptotically linearize in your model. Okay. So can you analyze what happens in these transformer models? Can you say something about what they converge to, or is there a well-defined width or depth limit? Well, we just talked about kind of depth. So we first looked at the infinite head size in H here. So if you fix the number of heads and take this to infinity, and there's sort of a symmetry problem where like all the attention weights and all the contributions from each attention head to the dynamics, they all end up kind of converging to the same thing. So there's this head collapse phenomenon. So all the heads kind of compute the same thing. You thought you had a multi-head attention model, but as n gets large, there's a symmetry problem, and all the heads kind of converge to the same dynamics. So you've lost kind of diversity across heads. So that's potentially bad because you're wasting parameters. The other idea is taking heads to infinity, and you can fix NH. And the point is you converge to some non-trivial mean field distribution over attention heads. So this is one entry in this attention matrix. The point is the measure is complicated. It's not Gaussian. So just like that feature learning distribution, just like the mean field distribution I had before where it was non-Gaussian. But the point is it's now consistent across heads. So like I'm actually converging to some well-defined limiting measure over these attention weights. Okay, and the dynamics here are very monotone. So like as I go to larger and larger heads, I'm sort of improving, and I eventually start converging to this infinite head limit. Okay, cool. Let me just like say, so like, you know, this theory is sort of nice in some sense. You can get some like qualitative stuff, but if you wanted to exactly integrate it on a real data set, let's say I wanted to integrate this on like a language model, the number of correlations that show up in this theory are really large, right? So this is kind of a big drawback because let's just say I had, like a spatial index or a token index. I have a data stream index X, and I have a time T, right? So in LLM pre-training, this would mean I'm tracking steps by steps, batch size by batch size, sequence length by sequence length. So this is just quickly, you just run out of memory. So this is not really an alternative to a parametric model in terms of like an efficient storage of information. But it does let you derive interesting results, like, for example, the symmetry of the heads collapsing and things like this, and understanding what happens as you take different limits. So we're going to focus on more of these like qualitative high-level insights from the equations. Okay. So MOEs are motivated by this. Yeah, so you do this routing, and it's motivated by the fact that, you know, we really want to use a sparse subset per token to minimize the sort of compute costs. So before people started doing this, one of the big dense models, the last big dense model people had, like almost 90% of the compute was happening in the MLP blocks. So people really were motivated to kind of like reduce the amount of compute per token in an MLP. Okay, and almost every modern model is of this type now. Okay. Oh, and the open question is how do you actually is there a mean field limit, and like how do you do it? Yep.
Sorry, just to go back, you said neural SDs versus neural ODs. What was the difference between this sets again?
Yeah, so that was whether you have 1 over square root of L in your branch or 1 over L.
Oh, okay. So what's alpha equals 1, ODE?
Alpha, yeah, so 1 over L is, I'm calling it ODE. I'm going to show an example in a second where there are some conditions where, anyway, yes, let's just say that's ODE. I was calling that ODE, and then 1 over square root of L, I was calling that SDE. Because you can think about if 1 over L is like my step size, right? And if I have a random part that's of order square root of step size, but independent, that gives me Brownian motion. That's like the Brownian motion part of the thing. So that's like the SDE flavor. And then the 1 over L should be like more like an ODE for the hidden states H. Good question. Yeah, thank you. Also, yeah, if there's any other questions, feel free to ask. Yeah, so how do we stably scale this up, and how sparse can we make it? Okay, so I'm going to do, for each block here, I'm going to do the following. So I have E experts, right? Each expert has a routing variable. So this is a hard routing. So this is a soft kind of component of the routing. So that's the sigma p. And then this theta is a step function. And the step function is going to take just it's going to be chosen with a threshold here, for example, that just selects the top k of these. So per token, this q is a different thing per token. But then there's a weight matrix. There's basically one MLP. So 2 layers, W1k and W2k, 2 layers of weights per expert. Okay. And so what is PK? PK is this router pre-activation. So how do I actually generate these router scores? I take my hidden state. For each token, I compute basically E different scores. So those are these PKs. And then the bigger scores should be like more important. And so I want to pay more attention to those. And I'm also going to include this router bias. That's this BK. That's going to be kind of important for us in a second. Because I'm going to ask the bias to do something different than the routing weights. Okay. So top K means only K of these things are non-zero. So I'm only going to have to compute the MLPs for K for capital K experts. And there's this problem with these models, which is that you really, if you do this naively, there's a load balancing issue. So like the number of tokens that get routed to each expert can kind of collapse. So like maybe this expert's getting like 80% of the tokens, and then this expert's getting like 10% of the tokens, and then this is only getting 10. So like that imbalance can be bad because like I'm sort of losing capacity in some sense because like it's like in the limit of 100% of the data points going just to this expert, it's like I just have a smaller model. So that's not good. So I kind of want my tokens to be distributed roughly evenly along this. So I want the number of tokens at K, at router K, to be roughly the same as the number of tokens at router L. Okay? So some people put in by hand some kind of auxiliary loss into their training procedure that encourages the model end to end during optimization to promote this load balancing. Okay, we looked at this. It was really hard to get this to work. In some sense, it's almost weird because it's like my attention layer 5 layers, my attention block 5 layers up is like helping me balance like through this gradient descent on this aux loss, helping me figure out how to balance this this token at this earlier layer or this later layer. So it's non-local and it's kind of annoying. It's very hard to kind of like do DMFT on this or like understand a well-defined limit. So what we were looking at is something that has shown up in a couple of other works, which is imagine each MOE block is responsible for balancing its own load. And the way it balances its own load is through the bias dynamics. So the Bs are going to be chosen so that we target basically the expected number of tokens per expert. So we're targeting this fixed level of sparsity. And I'm encouraging, I have an error rule, and the error rule is related to how different is the fraction of tokens that go to this guy compared to the expected fraction. Okay? So that's the rule for the biases. So the R's are trained with gradient descent, so the routing weights are trained with gradient descent, but then the biases are updated with this rule that encourages load balancing. And the biases are initialized randomly across all the experts, and that's kind of important for breaking asymmetry that I'll describe in a second. Okay. Yeah, so we're going to assume fixed sparsity. So, okay, this is maybe not ideal. You'd really ideally want to have k, the number of active experts, be constant, like 3, and I take number of experts large. That turns out to be hard. I mean, if you just thought about if you imagine that the router scores were IID random variables, that's more like extreme value statistics. Like if I did top 1, it's like asking, I have a very large number of random variables that are IID, and then I take the biggest one. That is a kind of different behavior than if I took an extensive fraction of those experts. So I'm going to look at the extensive fraction regime. So that's this fixed sparsity. So k over e is a constant. So 10% of the experts, I'm going to say, are active. Okay? Okay, so the claim is the following. So I can do the following thing. So I fix this kappa as a parameter. And then I can take a limit where the width in, the size of each expert, the number of experts, and the depth kind of converge to 0. So I want to look at that kind of joint limit. And okay, the claim is the following. So if I do that, there's a 3-level mean field theory. So at level 1, it's the stuff I've talked about a lot already. So this is the neurons and the kernels on the residual stream. So we already have a flavor of that. The new level is below that, there's this distribution over what I'm going to call expert states. So there are variables that are basically scalars and random across the distribution of experts. They don't converge per expert. They're kind of a random process that each expert has. So I'll call that, so for example, each expert has its own router preactivation, it has its own router bias, and it has some other states that show up in the DMFT calculation. And so, but these things are dynamic, so at initialization, the routing preactivations could be small. But as I train, and these are a bunch of different size models, but you can see as I train, I'm converging to some different routing weights. So, and that's because the routing weights are evolving over time. And what does it mean in this mean field limit to do top k? Well, with this kappa being fixed at a constant, it means I'm taking the top, let's say kappa is 10%. I would take the top 10%. So I'd look at the quantile threshold for the top 10% of the measure on this router preactivation. Right? So that's a well-defined operation now. So if you believe in this mean field limit, then if you think there's this mean field preactivation, then it's like I'd cut off this at so that the integral under this curve is 10%. Okay. And then the distribution over within expert neurons. So within an expert, there's also kind of the single side equations for neurons within the expert. Okay, but the point is, to go up the tree, I always do averages. So I do averages over these to get some of these states. I do averages over experts to get back to the residual stream. And then the residual stream generates the function through averages over the neurons in the residual stream. So everything sort of still concentrates in this limit. So the function still evolves in a deterministic way. Okay. This is just, so I didn't talk about MSR. So there's a way of doing this calculation with cavities, but sometimes it's nice to just sort of compactify everything as and there's a single DMFT action, S. So S tracks all the variables that should be self-averaging as under this joint scaling condition. And it doesn't really matter, but the point is you can show that there's sort of like a nice collection of variables that are deterministic in the limit, and there's a way to compute them through averages. And the way that you get, the final result you get by taking a derivative of S with respect to each of the variables you're looking for and setting that to 0. So you're looking at a saddle point of this action. Okay, and then what is top K? Top K means when I do an average over experts, I do an indicator of whether that expert preactivation is bigger than some threshold that is implicitly a function of kappa, so that the fraction of active states is kappa. So that's a self-consistent equation that you get. Okay, cool. Okay, wait. Yeah. So this is just showing that this works. So this you can vary expert count, you can vary you can vary size of each expert. This is just a toy soft routing model, and the soft routing is harder to get to work than the hard routing because there's a symmetry problem. So you really need bias diversity at initialization. in order to get a kind of diverse preactivation dynamics. But once you do that, you can see that there's an evolving router preactivation that's kind of highly consistent across model sizes. So that's nice. And then in real language model training, we also see, at least at the early time scale, very consistent dynamics. You can vary the width, you can vary the size of each feed forward block, so in E. You can vary the number of experts while also varying the active expert count, keeping sparsity fixed. All these things kind of collapse to one kind of universal curve. But then as you go to later time, there's sort of this regime where there's significant differences across model sizes. And you can see that you get pretty good approximate learning rate transfer across all these different dimensions. So that was nice. And yeah, and surprisingly, the limiting thing doesn't really depend on the ratio of width over the size of each expert. It doesn't depend on the number of experts or width or depth. It's just some universal kind of ODE process that depends on this ratio. Okay. Yeah, so there's an exotic limit that I noticed, which is like, if you instead don't take this to 0, but take this to some constant alpha, which is a really kind of exotic joint limit. It seems like what can happen is you can get an SDE process for the residual stream variables. So it's complete feature learning. It's complete feature learning in the sense that I described earlier, but it's also an SDE. So Datong's working on this. But you can also see this in a model that Louis Pierre and colleagues were looking at, which is this sort of residual stream network with a 2-layer MLP. And I think there, if you do n over this product of NE times L, if this converges to a non-zero constant, then I think you retain complete feature learning. So each of these blocks remains nonlinear, and the features inside this block update. But you have a kind of SDE joint behavior on the forward pass on the residual stream. And then from their paper, in our expert paper, we have an expert version of this. Controlling the ODE approximation requires controlling some kind of ratio like this, because at finite size, this is non-zero, but you want it to be 0 as you go to the limit. So you have this extra error term. But if you do an SDE, this error term disappears, and maybe you could get potentially faster convergence and maybe better transfer. So that's sort of open, but it's a kind of exotic scaling that's a little bit different than what people use in practice. So that's sort of an open problem whether this can save you compute, because most of the time people scale in, NE, and L linearly, which would result in this ratio going like 1 over n. Okay. We talked a lot about limits. Limits are like these ideal Platonic forms, but what I can fit on my computer is like a shadow of this thing. And so it's important, we motivated this by scaling. The finite models are not doing as good as the kind of infinite model. So we'd like to understand these kind of curves, right? But to understand that, you really have to understand finite size effects better than what I've done. So all I've described so far up to this point in the talk is describing infinite limits. Okay, and so sometimes things converge on some tasks and some architectures. They converge really fast. So this is ResNets on CFAR5M, so just an image classification problem. And these are different widths. And you can see that the dynamics are quite tight across widths over a long period of training. On tasks that are harder, so like more data, more output channels, right? So ImageNet, it's a more difficult problem than this problem. You can see that finite size effects kind of accumulate, and eventually like smaller models sort of start saturating compared to larger models. You eventually start to converge though. And then if you do like transformer training, you train a long time, and everyone knows this from transformer scaling research, right? If you train long enough, you start seeing small models sort of bottleneck, and large models sort of keep doing better. Okay. When it works, right? So so this is this ResNet setting. So this mean field density at initialization should be Gaussian. After training, it doesn't have to be Gaussian, but the things should be consistent across widths, and that's exactly what you see. And the kernels are also very consistent across model sizes. So the kernels go from this initial thing to some final configuration, and across a bunch of different model sizes, the final kernels are very similar. Okay. What about where it doesn't work? So there's sort of regimes where early in training, if you look at the convergence rate, so this is heads, attention heads, so just kind of like width, right? So I converge at a rate that's like predicted by this central limit theorem of fluctuations around the mean field theory. That's like 1 over width. If I go to later and later times, they start getting some other kind of scaling law. Okay? And if you go to a really late training in Wikitext or ImageNet, and you plot the loss as a function of width plus an offset, so this would be the loss I'd get at infinite width for that number of steps. You can see that it's non-universal. So the exponents you get for like Wikitext are different than the exponents you get for ImageNet. Okay, so where are these coming from? What sets these? And they seem to be task and architecture dependent. Okay, so, and then the last thing is, we had a spectral prediction for the weights, right? So when we were in the early time, the super wide regime, it was bulk plus spikes. If I train a width 1000 network with 1 billion tokens, right? So this is many, many more tokens than the width, right? Then I see that it doesn't just look like Marchenko-Pasteur. So at initialization, it's Marchenko-Pasteur. But after training, it doesn't look like the CFAR plot where it was Marchenko-Pasteur plus outlier. It looks like the entire spectrum sort of evolved in some interesting way. Okay, so we're kind of beyond. This is more like an extensive rank regime. Like the number of dimensions I've tried to push or change the weights is sort of larger than the kind of ambient dimension. So we need to try to build theories toward these extensive rank regimes. That's ongoing research. Okay. So I'm going to try building just a toy in like 10 minutes or so. I'm going to try just quickly describing a very simple toy model for the lazy limit of training, where you can try controlling the width effects, the amount of data, the training time, and build a toy model of neural scaling laws. So it's basically a random feature model because it's lazy. So it's basically linear in the effective parameters. But it captures a lot of interesting phenomenology about random feature models. And there's a bunch of works in this area. So ours is not the only work that's tried to use this as a toy model of scaling. But I think ours was kind of unique to sort of start looking at dynamics in this toy model, which can have interesting effects. Okay, so the idea is you have a kernel for your NTK at infinity. But then at finite size, and you have some eigenfunctions that are orthogonal. At finite size, you have some projected variant of these infinite features, right? Because you only have n parameters. So it's a smaller dimensional. So this is a rank n kind of kernel object instead of rank infinity. And the key properties are this A has to be random over initializations, and it has to have this kind of second moment structure. And the reason is that because Kn, this kernel, has to converge to the infinite width kernel. Okay. So let's treat A as random with this second moment and pretend everything else is just ID Gaussian. And you can do just a closed theory of this. So the idea is I can track, so I can expand my target function and my target function y and my student function in this basis of infinite width features. And then breaking that down, there's some target coefficient for the y. Oh, sorry, this should be y minus f. I flipped it. But this is the target coefficient for y, and this is the effective target coefficient for my student, right? So it's the projected A transpose on W. Okay. I sample random data. I populate the random data in these features. And then when I train this model, it's a product of two Wishart-like matrices, but these size have a different covariance structure. They have eigenvalues lambda. So if p goes to infinity, this turns into a diagonal matrix with an arbitrary spectrum lambda. This goes to the identity as n goes to infinity. Okay. And then the test loss is computing a certain norm of this vector. So it's a norm of this vector against this diagonal matrix lambda. Okay. So the key insight is if I look at this, right, if n is finite, then there's a null space here, right? And in that null space, I don't make progress. I want to decrease v. V is my residual error, right? And if there's a null space, then that means that some components of this v vector will remain non-zero even as n gets large, right? So that's kind of a key effect. Okay, and then can you do like some accurate description for a random matrix? So you can see this using the tools or the cavity methods, things like we talked about yesterday. You could do these averages like we talked about. Okay, one more observation is that on real data, these eigenvalues for kernels and these coefficients for the target functions often follow power laws. So here I'm just showing the eigenvalues for, let's say, a CNN on CFAR, and the eigenvalues for an MLP with just uniform data. You can see that there's power laws that depend on architectural properties of the model. Okay, so an ansatz that you could put into this toy model is basically that these things follow these power laws. And if you integrate this for random matrix A and compare to the kind of, let's say, DMFT predictions, that's the dashed lines, you can see that the models at finite size start off by following this infinite curve, but eventually saturate. So this is more like what you see in the real experiments. And you can predict that you can predict three different components. So you can predict a time scaling exponent, a width scaling exponent, and a data exponent. Okay? And, oh, sorry. Yeah, let me see. And then from these, you could work out like compute optimal scaling. So like, let's say you had enough data and you were doing one pass training. You could figure out like if total time times n is fixed, what's the optimal allocation toward t and what's the optimal allocation toward n. You can get the compute optimal frontier, which is sort of nice. Okay, so that's nice, but so we talked a lot about hyperparameter transfer across model sizes, but an open problem that's sort of still challenging, I think, is transferring across training time. So even if I do mu-p, even if I try to do things that are consistent across model sizes, if I train under SGD and I train longer and longer and longer, it seems like learning rates actually shift. And in practice, we'd like to ideally scale model size jointly with training time because that keeps you on that compute optimal frontier. So what explains this shift? How fast is this shift happening? So this was a paper by Microsoft, and they're claiming this goes like, optimal learning rate is like t to the minus 1/3. This is a paper from Apple, and they're claiming it goes like t to the minus 1/2. So we don't quite know. Can we develop a toy model of this effect, and maybe how to optimally set learning rates? So we're going to do the following. We're going to look at that same toy model I just mentioned, the power law random feature model, the dynamical model of scaling laws. And I'm going to imagine that I'm going to do an optimal control problem where I say, hey, I'm going to train for capital T steps, choose the best learning rate schedule. I could do either the best constant learning rate or the best learning rate schedule. So this is a calculus of variations problem over functions eta of t. Or in discrete time, it's like just an optimization problem over the eta t discrete vector. So under this power law model, you can write this functional in terms of a function chi, which is the sort of integrated learning rate from time t up to the end time. Okay, and you can see this is kind of a Lagrangian that depends on a boundary point and an integral that only depends on chi and chi dot. So this has like, you can use Noether's theorem or something to calculate the calculus of you can use calculus of variations to solve for the optimal shape. So there's kind of two regimes. So depending on A and B, right, these are these two exponents of the problem. There's one regime where you're dominated by the bias, and this is the most important thing, and only late in time do you need to anneal and change this. So in this regime, your base learning rate is as big as it can possibly be while remaining stable. And then after some amount of time TS, you anneal with a certain power law. That's related to this B. Okay? And the base learning rate is a constant, and then TS is, so the fraction of steps you anneal is a decreasing quantity with capital T. So it's a power law in T. Yeah. Yeah, so A was a spectral decay rate, so it's a power law exponent for the target coefficients in this eigenbasis of the kernel. And then B was just the eigenvalues themselves. So the kth eigenvalue is going like k to the minus B. So I have a power law spectrum for both. And when A is less than B, it means that it's actually really hard to optimize the bias, but the variance is relatively easier. If A is bigger than B, then the bias and the variance sort of term starts dominating if you use constant learning rate a long time. So like the SGD noise term becomes more important in this regime. And in this regime, there is a prefactor for your base learning rate that is a power law in capital T. This is kind of like the thing that we just saw from Microsoft and Apple. But it depends on your A and B, which could be like architecture and task dependent. It depends on your kernel's spectrum, right? So that's kind of interesting. And the shape of the curve, so that you anneal in a way that as T goes to capital T, this goes to 0. So your learning rate anneals to 0 by the end of time. But it goes to 0 kind of as a some kind of polynomial, 2b minus 1, where b is this exponent related to the spectrum of your features. Okay, so base learning rate decreases with training horizon. Annealing is polynomial. Okay, cool. So let's just show some simulation. So here's me taking my equations of motion and actually doing a numerical optimization over all the etas. So this is the optimal shape of eta for different capital T's. And then the scaling law you're interested in is actually the loss at the end at capital T as a function of capital T. And you can see if you do the optimal schedule, you're actually getting a better scaling law than if had you done constant learning rate. So even if you did optimal constant learning rate, you have a different exponent in this SGD-dominated regime. Okay? And then if your A is bigger than B, similar story, so you get a better capital T. So this is the capital T scaling law for the final time. That's a different scaling exponent than what you get if you did constant. And you can see that the shapes of the curves collapse if you rescale the y-axis by this capital T factor. So the base learning rates are decreasing as capital T increases. Okay. And we did one more thing, which was fun. So the bias-dominated regime seems potentially like hard to optimize. Turns out if you also include as a control parameter momentum, so you let momentum vary in time, and you do optimal control over the learning rate and the momentum, you can really boost the bias-dominated regime's convergence rate. So here's what I would get if I just did opt SGD. That's the black curve. I get a different scaling exponent actually for the optimal momentum when I'm in the bias-dominated regime. So here's a bunch of different configurations of A and B, and then I'm sort of fitting the exponent. I don't actually have a closed form for what this new exponent is, but so I'm fitting the exponent for a bunch of different things from the numerical optimization. And if I had just done opt-SGD, the exponents would be this blue line. I have a better exponent until A equals B, and then they go to the same thing. So in the SGD-dominated regime, there's no change, but in the bias-dominated regime, I'm getting a boost from optimized momentum. So optimal momentum beats optimal SGD in the bias-dominant regime. But yeah, you can also compare to the optimal statistical rate, and it doesn't quite reach the optimal statistical rate, so it's somewhere in between, which is kind of interesting. Okay, and then in the wild, we found two kind of examples that look like easy or hard, or look like bias-dominated or SGD-dominated. So first, so this image classification setting, so a deep ResNet on CFAR, this looks a lot more like the bias-dominated regime. So if there's no annealing, there's some shift, right? That's consistent with the hard phase, or the bias-dominated phase. But if you do some annealing for even a vanishing fraction of steps, the base learning rate transfers, right? So this is very consistent with this bias-dominated picture. In LLM pre-training, it's a different thing. So here, this is just showing, so if I do no annealing, that's the blue line. If I anneal at different capital T's, that's each of these curves. Okay, and this is near the optimal learning rate. And you can see that, okay, if I do no annealing, I shift to the left, my base learning rate shifts. But even if I anneal, there's some shift happening. So you don't perfectly transfer, even if you do annealing to 0. So okay, so that's kind of potentially interesting. Okay, so high level, we talked about this infinite width and depth limits of neural networks. They were described as averages over stochastic processes. Neurons could be noisy, but kernels are sort of self-averaging. Wide neural networks have deterministic macroscopic behavior that's independent of the microscopic details. And we were like showing that if you could stabilize things, make them more predictable, that could make pre-training a lot more predictive and reliable, potentially. And I think there's a lot more to do on this front, so people want to do longer and longer chains of thought. So like context length is another dimension you could look at. Pretty open. Missing ingredients. So the concentration effect that I need to exactly do this super wide regime, which is this overly optimistic Platonic form kind of limit, the super wide thing. As batch size times sequence length times steps kind of becomes comparable to width, you kind of become potentially closer to this extensive rank regime. And you might need different mathematical tools to describe the evolution of the network observables in that regime. And it might look like a different kind of DMFT. And yeah, we were trying to build toward a theory that maybe describes optimally or overtrained networks, where parameters is comparable to data. Right? That's kind of the regime where people stop training. And this is worse performance than if you had just taken parameters to infinity and studied the data scaling law, right? Which is kind of what we were studying, but this is maybe more realistic and harder to do the math for. And then can we figure out this across token horizon thing and more tractable, more realistic models beyond this toy model of scaling laws? Okay, and I just want to thank everyone, all these people that collaborated, including some people here like Lorenzo and Mufon. And yeah, so thank you guys for your time.
So thank you, Blake, for the very nice talk. We have time for some quick questions. Okay, so let's thank the speaker again.